A special role in the theory of colimits in category theory is played by pushouts. On the one hand, these are among the simplest non-trivial examples of colimits, and on the other hand, they are the building blocks for colimits of any shape. The most common way to understand pushouts intuitively is to see them as gluing. To construct a pushout from this diagram, first draw B, A, and C separately, and then identify each point A with both F of A and G of A. The dual notion is that of a pullback. Pullbacks are limits of diagrams shaped like a corner. Surprisingly, reversing the arrow direction messes up our intuition, and there is no simple way to visualize a limit. Then how are we supposed to think about pullbacks? First of all, if pushouts are like unions, then pullbacks are like intersections. Well, at least if the involved arrows are subobject inclusions. This diagram is a pushout diagram, but it is also a pullback diagram. This is a special, but quite common case that is useful to keep in mind. Another common way is suggested by the very name of the pullback. The focus of this perspective is the notion of the fiber. Let's go into the category of sets, and define for a map F from A to C the fiber over the point C as the preimage of C under F. We can visualize the map F by hanging above each point of C the fiber over it. The map F now just projects down. Note how this perspective allows us to rewrite every function as a straightforward projection by replacing its domain with the graph of that function. Now returning to pullbacks, imagine that B is just a one-element set. The map from B is then just hitting some point of C. Then, what pulling back does, is it pulls the fiber hanging above this point over to the point of B. We see the picture on the left as a map, just as we saw the picture on the right. Now, an arbitrary B consists of a bunch of one-element sets. To find the pullback, you now do the same pulling of the fiber for each point of B. Thus, taking a pullback amounts to this procedure of fiber stealing. For example, every line bundle arises as a pullback. Informally, a line bundle over a space S is a linear vector space growing from every point of space S. This is formalized as a projection onto S from a certain space, which is the totality of those vector spaces. The fiber over a point is now the line that is assigned to it. Turns out that there is a bundle that gives rise to any other, and our perspective on pullbacks makes the idea here clear. The total space of this bundle is essentially the space of all possible abstract lines. Note that having such a space, we can encode an assignment of a line to every point by sending every point of S to the corresponding line. Now pulling the fiber back over this point produces the desired fiber bundle. A more symmetric perspective comes from asking what happens if C is a one-element set. In this case, the pullback is the Cartesian product of A and B. Then, an arbitrary C is a bunch of one-element sets, and the pullback is the union of the products of fibers over each of those points. This perspective is quite general in the sense that there is a broad class of categories where pullbacks distribute over coproducts. However, I am not sure it is a very useful way to visualize in practice.